Okay. All right, so if you're watching this, you have completed your test, and now today we're going to just get the data for this first lab. And so here's the whole point. I know you all probably haven't watched the lecture, but here's what's going to happen. What we're going to do is going to collect data in terms of where this cart is as a function of time. Then we're going to draw two different graphs. We're going to draw a position time graph, and then we're going to draw a velocity time graph. Okay? Now, this will all eventually make more sense to you. Okay, but here's a condensed hour-long version of lecture into like 5 minutes. So the position time graph allows you to keep track of where an object is as a function of time. So you start off with a reference point. In this case, the reference point, what you guys are going to have is that you guys are going to have a little timer like this. It's called a spark timer. Because oddly enough, it keeps track of time and it makes little sparks, so we call it a spark timer. And what it's going to do is it's going to pull a piece of tape through here that's going to be attached to this machine that's going to be moving down the road. And we're going to keep track of where this thing is as a function of time. So we're going to define this as the reference point. Okay, so we're going to define where everything is relative to this. So reference points are important because that's how you define where you start. So, like for example, in the lab I talk about Ellie being, oh hey, where's Ellie in the room? Okay, so she's going to say, oh well, I'm in front of the F equals MA sign, or I am 6 meters away from the door, or I am 4 meters away from the water bottle. It's something, it's a fixed point. But then if she begins to move, then we talk about her change in her position relative to that reference point. Okay, so that's the first thing we have to establish. Then, and here's what's going to be important about a position time graph. Normally, that position is going to be in meters, and that time is going to be in seconds. So if it's a straight sloping line, and we've talked about this already in one of the assignments, the slope of this line would be change in y over change in x, which would be meters per second. So basically, if you look at this graph, the slope of any position time graph is going to give you velocity. So if the slope is the same all the time, that means the velocity is the same, which means it's changing position the same amount in each interval of time. If the line is curved, like this, okay, then that means that the object is slowing down because the curve is becoming more flat. If the curve, which is what's going to happen on your guys' lab, you guys should end up with a curve that actually is going to end up look something like this. Okay? So if this line is becoming steeper, that means that the slope is becoming steeper. That means that the object is going faster. So on any motion that you have, you only have one of three options. It's either speeding up, it's slowing down, or it's moving at a constant velocity. Okay, that's it. There's nothing else. Those are the only three things that can happen on a position time graph. Now, that constant velocity might be at rest. So if you have a horizontal line on a position time graph, that just means that you're staying at the same place and you're not moving and you don't have a velocity. Okay? All right. Now, the other graph you're going to draw is a velocity time graph. And your velocity time graph is going to look something like this when you get done. But here's what's important. This is going to be in meters per second, and this is going to be in seconds. So if you find the slope of this line, you get meters per second, which is meters per second squared, which is acceleration. So here's 0 meters per second, so the slope of this line is going to represent acceleration. So remember, here's the first thing I want you to get out of your mind. Acceleration does not always mean that you're speeding up. Acceleration just means that your velocity is changing. Okay, that's all. That's all it means. So in this situation, the car's going to start at rest, and it's going to speed up because I'm going away from this line, which represents 0 meters per second. So if this line is going away, that means it's speeding up. If this line is coming back towards 0 meters per second, that means that it's slowing down. If you have a horizontal line, that means that your velocity is constant and it's not speeding up or slowing down. So you have only one of three things that can happen on a velocity time graph. You're going away from 0 meters per second, which means you're speeding up. You're approaching 0 meters per second, which means you're slowing down. Or you're a horizontal line, which means that you just have a constant velocity. So the beauty of every motion that you're going to study in this class is only one of three things. You're either speeding up, you're slowing down, or you're moving at a constant velocity. Now, one of the things you will hear on this lecture that I beg of you, you have to watch this lecture, is that if an object changes direction, okay? So let's say I take this cup and I move it here and then I move it back over here. If an object changes direction, there's three things that has to happen. It's got to slow down, stop, and then speed back up. Okay, that's what has to happen. If I take this weight and I throw it up in the air, that's the perfect example. It slows down on the way up, it stops, and then changes direction, and then it speeds back up. And the other thing that happens, and again, I laid this out in great detail in the lecture. If something changes direction, the velocity has to change sign. That's done with a banjo, just as a teaser. So, if your velocity changes sign, you change direction. So, how that's shown on a velocity time graph is that what will happen is that we'll cross through 0 meters per second. Because if this line crosses through 0 meters per second, it means you're slowing down, you're stopping when you hit 0, and then you're speeding back up. Okay? So if something changes direction, three things have to happen. You have to slow down, stop, and then speed back up. Okay, so here's what you need to do in terms of this lab. So what you're going to have is, hold on. Or I can just use that tape right there. Okay. So here's the deal. You need, and there's dispensers back there, and there's 8 of you, so let's do like 2 groups of 4, that'll work. So you need to pull off a piece of tape about yay long, okay? It's a technical term, about yay long. Like this, okay? And make sure there's like a dull side and a shiny side. Make sure the shiny side is up. Then on the tape timer, there's a little arrow that points in the direction that you need to feed the tape. So you're going to feed that through. And lay this out. Now, you want to make sure you know which direction that your machine goes. So when you turn it on, you want to make sure that it's going away from your tape timer, like this, okay? Otherwise, it climbs back over the top of it, and that's just awkward. So, you know which direction it's going to go. Tape this on, like so. Have this stretched out. Now, this timing is important. On this tape timer, there's 2 buttons. One that says power on and off, and the other one has 10 or 60 hertz. That tells you how many vibrations it makes per second. Make sure that it's set on the 10 hertz setting. Okay? Make sure that it's on the 10 hertz setting. So you're going to put it on, make sure it's like that. So turn on the tape timer first, and then turn on the machine. Okay? Tape timer first, then the machine. So we'll turn that on, okay? And then we'll go. Lost that. Turn on that. Now, you guys will obviously go a lot farther because you have bigger tables than that. So what's going to happen is that when you look at this tape timer, you're going to have a series of dots. And that's where it was making the dots when it was just making them and nothing was moving. Then, what you're going to do is you're going to see these dots getting further and further apart. So, getting the data is simple. Take that on, you just need to run 1 tape per group. Now, what you're going to have to measure is this distance between the intervals. You can have rulers back there. So we're going to call this first gap between where this is and this first set of dots the first interval. So you're going to measure this distance, okay? So if you want to, you can come in here and label this, okay, here's 1, there's 2, there's 3, 4, whatever, okay? So then, as you're going across, then on your lab, and you're going to go all the way through interval 12. And so on your columns, you've got time, displacement, total, and then velocity. Now, I've already put the labels for these columns at the top. You don't have to write these units each time. I already have them labeled. So you're going to measure this distance from this first set of dots to interval number 1. So I'm just let's say that that's just 1.20 centimeters. Okay, make sure that you're going to, when you measure this, you're going to know the tenths and you're going to estimate the hundredths. So your total displacement is how far you have gone at the end of each interval. Well, at the end of the first interval, that's all you've gone. Okay, is 1.20 centimeters because that's it. Now, on the velocity, we're going to make this simple. Your velocity is going to be whatever your distance is traveled in that interval. Now, in reality, it's technically not because you're actually speeding up a little bit, but we're not going to mess with that for now. So, whatever you have as your distance in that first interval is what you're going to have as your velocity. So I'm going to have this as 1.20 centimeters per interval. Now, let's say in the second one, you're going to go a little bit further. So when you measure the second one, you're going to go from this set of dots to here. Okay, don't measure all the way back from the beginning. It's from this set of dots to this set of dots. So let's say that that's 2.00. Now, this is going to be like a running total, because this is going to be how far I've gone from that first set of marks. So this situation, that's going to be 3.20, but then my velocity here is going to be whatever my displacement is, so that's going to be 2. So that's going to be 2.00. Now let's say the next one is 3, I'm just making up the numbers, that's going to be 6.20, that's going to be 3. So what you should theoretically see is that if these machines do eventually kind of level out, so these velocities should become relatively constant, okay? There's going to be a little bit of variance, but it's going to be pretty close. So in terms of collecting the data, that's all you need to do. Then on that sheet of graph paper that I gave you, here's your sheet of graph paper. You're going to draw 2 graphs. You're going to draw one where it's going to be total displacement, and then here are your time intervals. So that's going to go from 0 to 12. And when you get done, that graph should look something like this. Graph total displacement, because you're keeping track of how far it's moved from that reference point throughout the entire thing. Then the second graph you're going to do, and you can put these all like on the same paper. That's why I just gave you one. And then the second one you're going to do is velocity versus intervals. And that graph is going to look something like this. Okay, it depends upon your data. But this graph is going to start at 0 because the machine isn't moving. And then it's going to speed up, and then it's going to have relatively constant velocity. Okay? So there's this. So here's what I'm going to make a more detailed. I got to turn you loose so you can have time to get your data. I'm going to make a more detailed explanation of what I want on the graph that I'll dump out on YouTube so that you'll have a better idea of what's happening with this. This lab is going to be due on Wednesday. I've sent you all out the schedule. So here's what you need to do. right quick, go back, work in 2 groups of 4, generate the tape, get everything measured, and make sure everybody has that column, and then you can do everything from there. Watch the YouTube videos, okay? That's going to be important. All right, go, be free. Press that silver button again, would you? Right. Okay, so after you get done collecting the data, and if you're watching that, you already have your data. So you had your tape, and you had those series of dots, and then these dots are going to start to get further and further and further apart. So what you want to do is, again, you're going to measure like that distance between that first set of dots to here, okay? So I measured it and I had 0.65 meters. The second interval, I'm going to go from here down to here at 1.24, and then so on, 1.9. So the total displacement is the running total. So I took this displacement here of 1.24, added that to 0.65, and that's how I got the 1.89. So from where I started, I'm at 1.89 meters. Now, your velocity in centimeters per interval is going to be whatever your displacement column is. So, in reality, this is a little bit off, but it's not really enough to mess with in terms of what we're going to do. So, this is why here in the second interval, I was 1.24. I want to say I want 1.24 centimeters per interval. This is going to be the running total. So this is going to get all added up here. You're just going to keep going down like this. These columns will be the same. So when you get down below, when you get to number 4, okay, or let's just kind of go through these. You're going to make a position time graph. So number 1, this position time graph is going to look something like this probably when you get done. You're going to have total displacement versus time, and you're just going to go up through 12 intervals. And when you get down, it's going to look something like this. And then you're going to have a velocity time graph, and that's going to look something like this. Probably won't be exactly horizontal. Now remember, this is showing how fast you're going as a function of time. This is showing where you are as a function of time. Okay? So this is what these graphs are going to look like. Now, on the velocity time graph, I'm going to tell you, indicate if the car is speeding up or slowing down by drawing arrows. So here's the deal. So you're going to come in here, and you're going to draw, like here, basically if this line is going away from 0 meters per second, you're speeding up. Okay, hey, I'm going to draw an up arrow. Here it's slowing down. I'm going to draw a down arrow. Okay, that's all you have to do. If it's completely horizontal, there's nothing to draw. So basically, you're either speeding up, and you're going away from 0 centimeters per interval, or you're slowing down and you're approaching them. Okay? Now, then on number 3, it says indicate if the acceleration is positive or negative at each interval by using either a positive A or a negative A. Well, imagine that you're back in a math class and you have an upward sloping line. That has a positive sloping line, so you're just going to come in here and go, okay, hey, in that region, that has positive acceleration. This region here, you're going to have negative acceleration. Now, in this lab, okay, because of the fact that you only have, oh, sorry about that. Because you're always going to have positive velocity, we're not going to change the direction. So either your acceleration is going to be positive or negative. So basically, if it's an upward sloping line, you put a positive A. If it's a downward sloping line, you put a negative A. And draw this big enough. Remember, you're going to have to do this with like a key. You don't have to take a picture of this and send it to me. So make sure that I can clearly see on your graph these regions. Right? If you want to get creative, and let's say that you're into colored pencils, and you want to shade this and go, hey, if it's shaded purple, that means that it's a positive acceleration. If it's shaded green, that's negative acceleration. And put a key up here so that I know what it is. If you're into that, fantastic, okay? I don't care. Just don't make me guess about what you've drawn. When you get to number 4, you want to calculate the average velocity for the total trip, okay? So, and I'm telling you right here, take the total displacement and divide it by 12. Because your average velocity is position final minus position initial divided by the total of number of intervals. So in this case, this is 12. So your initial position is 0. Your final position is whatever you have here from this middle column, which is your total displacement. So that's why I said you're going to take your total displacement, divide that by 12. Notoriously, it's probably going to be something around 2. So when you do that, then you're going to go to your velocity time graph and you're going to draw a horizontal line across like this at whatever you get for your average velocity. It's probably going to be around 2, something like that. Okay? So you're going to draw that line across like this. Boom, there you go. Do that as a dashed line. Again, if you want to do this in a different color, hey, fantastic. Label it. Just make sure that I know what it is. Now, on number 2, what is that area between the x-axis and the line represented on a velocity time graph? We went over this. It's in your notes, but that's going to be the displacement. So when you look at this graph, if you could calculate that area underneath that graph, that's going to get you total displacement. Now, on 5 and 6, these are going to be the most critical ones that you have to answer. So at number 5, I've got write an explanation to describe what can be concluded by the shape of this precision time graph, all this good stuff. So what I'm looking for, okay, so here's going to be this total displacement versus time, this first graph. So you would say, hey, at the beginning, the slope is increasing, which indicates that the car is speeding up. And then once it reaches a constant velocity, then the slope becomes constant. Okay? So this is what you want to point out. Notice that I've given you some lines there. Okay? You want to go through this graph, and again, on any position time graph, you only have one of 2 options. Either it's a straight sloping line, which indicates that you have constant velocity, or it's a curved line, which indicates that it's speeding up or slowing down. Okay, that's it. There's nothing in between. So that's what I'm going to look for on number 5. Now, notice that, look what I want. I say explain any changes in the slope and what can be concluded. Explain any regions where the slope is constant. So what is, if you have a constant slope, what does that mean? Okay? Now, on number 6, you're going to do the same thing. But notice that I'm talking, and both of these, I want to point out one thing. We're talking about the shape. Okay? So you, oddly enough, you want to reference the shape of the graph. So on that position time graph, you would say, hey, at the beginning it's got a shallow curve. Oh, hey, guess what? That's when this thing is speeding up. Oh, the next part, the shape of the graph is a diagonal sloping line. Oh, that indicates constant velocity. Now, the same thing's going to happen here on this velocity time graph. So you would say, oh, at the beginning, the graph is raising up, going away from 0 meters per second. Oh, that's when the car is speeding up. So one of the things that you have to understand is that your position time graph and your velocity time graph have to show the same thing happening at the same time. Okay? So what's going to happen here is that when this graph is sloping up, indicating that it's speeding up, that's when this position time graph is curved, sloping upward. When this graph becomes relatively horizontal, that's when this graph becomes a straight sloping line. So a straight sloping line on a position time graph correlates with a horizontal line on a velocity time graph. Okay? That's one of the most important things that you have to get straight. Okay. So anyway, so number 6, talk about the shape of the graph. On number 8, if the slope of a velocity time graph changes sign, does that mean that the car has changed direction? So what I'm asking for on this one is that if you come up here, and again, I'm talking about the sign of the slope. So here I went from positive acceleration to negative acceleration. So what I'm asking is that at that point, does this cart change direction? Okay? That's the whole point of that question. Now, think this through. Remember, if something changes direction, the slope of your position time graph has to change sign because that indicates that your velocity has changed sign. And you have to do three things to change direction. You have to slow down, stop, and speed back up. So ask yourself, when you're looking at this on a velocity time graph, does that indicate a change in direction? Okay? Does it fit the criteria that you have to slow down, stop, and speed back up? Keep in mind this is a velocity time graph, not a position time graph. Then on number 10, you're just going to finish out those graphs. So there you go, kids. So that should give you enough of an explanation to finish up the lab. I'm done. You're on your own. Be free.